Hey, what's going on, guys? Let's do this problem right here. The question is asking two protons 2 times 10 to the power of minus 10 meter apart are pushed together slowly until they are 3 times 10 to the power of minus 15 meter apart. How much work is required? If they are let go, how fast will they be moving when they are returned to their original position? Okay, let's see how we can do this. First of all, they are saying the protons so we have two protons right here. In the first condition, in they are 2 times 10 to the power of minus 10 meter apart. So the distance between is 2. So let's say R1 is equal to 2 times 10 to the power of minus 10 meter. And then they are saying apart are pushed together slowly until they are 3 times 10 to the power of minus 15 meter apart. So they are pushing these two protons to bring it together, and this distance is 3 times 10 to the power of minus 15 meter, right? Meter, and this is R2. So this is R2, and this one right here, these two are R1, right? So we have pushed this one from here to here. So the question is asking about how much work is required. So to find the work is required, what we can do, we can find the potential energy on top that during this distance, and we can find the potential energy in this distance, and if we calculate the difference, that's going to be the work done, right? That's going to be the work done. So let's see how we can calculate that one. So the equation for the potential energy is P. So let's do this one first. P for the first distance, the longest distance. So P E1. So the equation is K Q1 Q2, K Q1 Q2 over R1. Since we are taking this distance, that's why we are talking about R1. So K is always 9 times 10 to the power of 9 Newton meters square per Coulomb square times Q1. So this is a proton, right? Proton charge is 1.6 times 10 to the power of minus 19 Coulomb. So this is a proton and this is also a proton. So we have to multiply both of them. Both of Q1 and Q2, both of them are going to be 1.6 times 10 to the power of minus 19, right? Minus 19 Coulomb. And in the bottom we are going to have the distance, that is 2 times 10 to the power of minus 10 meter. So this is for the first one, and if you calculate this one, you will get 1.15 times 10 to the power of minus 18 joule. So this is the potential energy when they are in this distance. So let's see what happens when they are pushed together and bring it to this distance. What is the potential energy right here? So let's see how we can calculate. Same equation, K Q1 Q2 over, in this case, R2, the distance is difference, so R2, and in the top all the values are going to be same because we are going to have protons, both of them are protons still. So 9 times 10 to the power of 9 Newton meter square Coulomb square times 1.6 times 10 to the power of minus 19 Coulomb times 1.6 times 10 to the power of minus 19 Coulomb divided by this distance, that is 3 times 10 to the power of minus 15 meter, and that's going to give us 7.68 times 10 to the power of minus 14 joule. So we have calculated the potential energy for this situation and this one. Now to find the work, we have to calculate the difference. So let's calculate the difference. W is equal to PE2 minus PE1. So here we have PE2, that is 7.68 times 10 to the power of minus 40 joule minus 1.15 times 10 to the power of minus 18 joule. And if you calculate the difference, that will give you 7.68 times 10 to the power of minus 14 joule. So this is the work that is done. So this answers the first question right here. So that is the question, right? How much work is required? And then they are asking, if they are let go, how fast will they be moving when they return to their original position? So we can find this one by equating these two things. Like, so let's say this is B part. So B part, we can equate the initial potential energy and final kinetical energy, right? Since kinetical energy is dealing with the velocity, so we can equate to find the velocity. So let's see how we can find it. Initial potential energy is the work done, like this is the initial potential energy, right? The work done to bring it to this position, that's going to be the initial potential energy. So we can replace that one with 7.68 times 10 to the power of minus 14 joule is equal to E final, that's half mv square. Half mv square is, this is final kinetic energy, or you can put Ke, same thing, E final. Okay, so now we can flip this around. Maybe I use a different color, right? Okay, here we go. So we are trying to find the velocity right here. So velocity is equal to 2 times 7.68 times 10 to the power of minus 40 joule, and also this is also we have to multiply by 2 right here, because we are dealing with 2 protons moving away, right? So we have to multiply this one by 2, and here this 2 cancels. If we do that, these 2 cancels, and we will only have mv square. So mv square, so therefore this is going to be, there's no 2 going to be right here. So this is going to be dividing by mass, right? Mass and square root. And mass of the proton is, so let's continue right here. I'm copying this one down. So in the top we are going to have 7.68 times 10 to the power of minus 14 joule, and the mass of the proton is 1.67 times 10 to the power of minus 27 kilogram. So this is the mass of the proton, and if you calculate this value, let's choose this one. Okay, if you calculate this value, you will get 6.8 times 10 to the power of 6 meter per second, and that is the speed, that's the velocity. So that is the question asking, right? How fast will they be moving when they return to their original position? So this is how we do these kind of problems. I hope you guys like this video. See you next time.